Okay, so in the first part of the talk, we talk about balanced neutral manifold, we talk about Tautness, we talk about foliations. And so in the second part, I'm going to present my main theorem and also the idea to prove it. Okay, so before I present my main theorem, there's one last definition. So about the depth of the foliation. Right, so let's say suppose F is of course we work with codimension 1 foliation, or let's say it's Taut. Well, it's not necessarily Taut foliation on the balanced neutral manifold. And so, well, we define the depths. So inductively, the first, compact leaves of F are said to have depths 0. Right, so if a leaf is compact, then it's said to have depth 0, and so if L is a leaf of F, and we know that the closure of L contains only leaves of depths at most k minus 1, and L, the closure of L contains at least one leaf of depths k minus 1, then we say that L has depths k. Right, so we define depths inductively. So the depths of F is defined to be the maximum depths of all leaves of F. Right. So for example, well, if we have a product neutral manifold, for a compact F, then, well, each leaf is of course, then there is a product foliation, so that the leaves of the form T times F, right, so F is Taut, and the depth of F is 0, right, because all leaves are, of course, they're just F, and so they are compact, and so this is an example of depth 0 Taut foliation. So the theorem of Gabay says, well, if M and gamma is Taut, then M and gamma admit a finite depth Taut foliation. Right. But the problem is, well, Gabay only proved the existence of finite depth Taut foliation, but he didn't give any bounds on the depths. Well, can we find any bounds of the depths of the foliation. Right, so recall in the first part of the talk, we talked about the depths of suture manifold. That's the steps of suture manifold decompositions, making M and gamma into a product suture manifold. So we do have a bounds on the depths of suture manifold, but however, well, prior to the main theorem I'm going to talking about, well, there's no effective bounds for the depths of Taut foliations. So there's only a conjecture by Uhash that, well, if H2 of M is 0, and well, of course M and gamma is Taut, and the rank of the suture fluor homology of M and gamma is smaller than 2 to the k plus 1's power, then he conjectures that, well, the balanced suture manifold admits a Taut foliation of depths at most 2k. Okay, so, well, currently we don't know how to whether this conjecture is true or false, and the best thing we can achieve right now is the following theorem. This is the main theorem, which I proved last year. So if we have given the same condition, well, let's just say, well, if the second homology of M is 0, and of course we work with Taut balanced suture manifold, and either the sutured Instanton fluor homology of M gamma, let's just say the dimension, is at most 2 to the smaller than 2 to the k plus 1, or the sutured fluor homology, or this from Hegel fluor theory, and the rank is having the same bound, then, well, M and gamma admit a Taut foliation of depths at most 2 to the k plus 6 power. Right, so you can see, well, the conjectural depth is 2k, but right now we can only achieve 2 to the k plus 6, so there's a big gap in between. Right. Okay, so as a corollary, well, the main theorem also gives us a mysterious relationship between the representation varieties of knot inside 3 manifold with the depths of Taut foliations in the knot complement. So as a corollary, well, if L, also let's see K, inside S3 is a knot, and so we can consider the irreducible SU2 representations. Rho from the knot complement to SU2, so that rho maps the meridians of K to this element. Well, this is a rank 4 element inside SU2. So now let's say, suppose these homomorphisms are all non-degenerate, and well, the number of the conjugacy classes of such homomorphisms has a bound 2 to the k plus 1. Well, then the final conclusion is that, well, the knot complement S3k, which is obtained from S3 by digging out the tubular neighborhood of the knot, this admit a Taut foliation of depths at most 2 to the k plus 6. Of course, well, it is conjectured by Kronheimer and Morfka that we could have this 2k instead of this very big bound 2 to the k plus 6. All right, so yeah. All right, in the last 15 minutes, I will roughly explain how we can achieve this Mann theorems, right? So how can we achieve the bound for the depths from Instanton fluor homology? So, okay, so well, let's see. We first talk about this SHI. Well, this is the sutured Instanton fluor homology, and it's introduced by Kronheimer and Morfka in 2010. So it associates a finite dimensional complex vector space to any balanced suture manifold. And it has many important properties. For example, well, this is non-trivial if M and gamma is taut. And well, if the second, well, let's see, if of M is 0, then it's of rank 1 if and only if M and gamma is a product. And also, well, if we have a suture manifold decomposition, then the suture incident fluor homology of the decomposed suture manifold is a segment of the original. Right, so the suture incident fluor homology has many good properties. So yeah, they're almost all due to Kronheimer and Morfka in the same paper. Well, they introduced this suture incident fluor homology. So, but how can we use it to bound the depths of Taut foliations? Well, let's go back to Gabai's original theorem. So Gabai says, well, if M and gamma is taut, then, well, M and gamma admit a finite depth Taut foliation. Okay, yeah, so this is Gabai's original theorem, but the idea to prove it. Right, so because we have a Taut balanced Suture manifold, and this means, well, there is a hierarchy or a sequence of balanced Suture manifold decompositions. So that this is a product Suture manifold. Right. And from the above example, right, so the product Suture manifold adapts 0 Taut foliation. Right. So what Gabai proved is that, well, if we have a Suture manifold decomposition, so that they are both Taut, and, well, M prime, gamma prime admit a finite depth Taut foliation, then we can glue this F along S to obtain a finite depth Taut foliation on the original Suture manifold on M and gamma. Right, so if after the decomposition there's a finite depth Taut foliation, then we can glue it along this decomposition. But the problem is that, well, a priori, there is no bounds on the increasing of depths. Right, so in Gabai's original discussion, well, it's hard to know like how much, well, the depth of the Taut foliation will increase during this gluing process. So that's why we could only obtain finiteness, but not a bound. Okay, so then how can we prove our main theorem? Right, so this is related to one theorem which I introduced in the first part. So let me circle it here. Okay, so let me do this. Right, so in the proof of the theorem, right, so the proof is that we have a bound on our on the depth of the Suture manifold being 2k, and this 2k means, well, we decompose 2k steps to make M and gamma into a product Suture manifold. Right, so in the proof of the theorem, well, we constructed a 2k step decomposition or hierarchy of this M and gamma. Right. So yeah, and essentially speaking, well, what I did is to analyze this 2K step of decomposition to understand what's happening for so how much can the depth increasing for each of the steps. Okay, so there's 2K steps of decomposition, right, falls into K stages. Right, so we have K stages of decomposition, and in each stage we have two decomposition. Right, in each stage we have two decomposition. Right, so we have K stage, and in each stage we have two decomposition. So in total we have 2K decomposition. So right, so say we say for each stage we deal with M2K, gamma 2K. Right, in the right, so of course M0, gamma 0 is just our original M and gamma. As in the 0 stage, we deal with our original M and gamma. Right, the first decomposition right, the first decomposition will reduce this reduces the dimension of SHI by half. Right, so the dimension is at most half of the original one. Okay, so right, and right, so I don't have time to explain the details, but right, so we study how the surface looks like, and actually we can apply a lemma by Gabay thing that will so if M2I plus 1, gamma 2I plus 1 admit a Taut foliation of depths L, then if we glue with this special surface, we could only increase the depth by 1. Right. So right, so in each stage we have two decompositions, but the first decomposition of this 2 only increase the depth by 1. So the second decomposition is tricky. Right, so we got M2I plus 1, gamma 2I plus 1, and decompose along some surface. Right, so S2I plus 1 goes to M2I plus 2, gamma 2I plus 2. And so this decomposition, well, does not change the suture fluor homology. But our S2I plus 1 has a very special property that is a union of annuli. Right. So where each AJ is an annulus. Right. So the first decomposition will reduce the dimension by half, but and it's also very good. So it will only increase the depth by 1. But the second decomposition does not change the fluor homology. Right. But and also it's very good as it's a union of annulus. All right. So and the very small lemma is that, well, if we're gluing a Taut foliation M2I plus 2, gamma 2I plus 2 along an annulus, AJ, then the depth increases by a constant. Right, by some constant C, right? So there is a constant, well, it is independent of the annulus. Well, this ring manifold. So just some constant. So so what we need to do is we glue this Taut foliation along this union of annuli, but as we glue along each annulus, so the depth is increased by a constant C. So the last lemma we will need is that, well, this number of the annulus is bounded by, well, let's just say, so this N2I plus 1 is at most some constants times the dimension of 2I plus 1, gamma 2I plus 1, right? So the number of this annulus is bounded by a constant times the dimension of the suture fluor homology. All right, so yeah. Okay, so let me go through this again, right? So we have a decomposition of our M and gamma into a product suture manifold by at most 2k steps. And this 2k steps is a k stage, and in each stage we have 2 decompositions. And in the first of that 2 decomposition, well, the depth is only increased by 1. And for the second of this decomposition, well, we have union of annuli, and each annuli will increase the depth by a constant. And the total number of the annuli, right? The total number of the annuli is bounded by a constant times the dimension of the suture fluor homology. So if we assemble all these pieces together, we will get this 2 to the k plus 6 in our main theorem, right? So here, this is like 2 to the k plus 1 times 32. So this is not a very sharp bound, this 32 is this constant, but I just want to make it like a simpler form, so I just put it 32. Okay, so yeah, I will end my talk here, and thanks everyone for listening.